When an unstable atomic nucleus decays, it ejects an alpha particle, a dense, high-energy cluster of 2 protons and 2 neutrons tearing into space. Intuition suggests that moving projectiles behave in a fairly straightforward way. As they travel through a medium and collide with obstacles, they lose momentum, and their rate of energy transfer steadily drops until they finally stop. Alpha particles defy this assumption. Instead of a steady decline, the amount of destructive energy they death into their surroundings compounds over time, culminating in a violent, localized spike at the exact moment they run out of momentum. This 2D line graph charts that exact trajectory. Penetration distance is on the x-axis, and energy deposition is on the y-axis. Notice the flat travel followed by a sharp upward spike right at the end of the particle's track. This terminal release of energy is known as the Bragg peak, and it is a foundational concept in health physics and radiation oncology. To understand why a decelerating particle suddenly deposits maximum energy, we have to look past the top-line phenomenon and deconstruct the particle's mass, its electrical charge, and its shifting velocity. The Bragg peak appears as a macroscopic anomaly, but it is completely dictated by the strict microscopic kinematic rules governing how the particle interacts with atoms as it slows down. Immediately upon emission, an alpha particle possesses 2 defining physical properties. It carries a strong positive charge of +2 and maintains a massive physical profile. That mass is crucial. An alpha particle is roughly 7,300 times heavier than a standard orbital electron. As this massive projectile plows through solid matter or air, it rarely interacts with the dense nuclei of the target atoms. Instead, it interacts almost entirely with their vast, negatively charged electron clouds. Because of the extreme mass differential, colliding with these tiny electrons does absolutely nothing to deflect the alpha particle's trajectory. It acts like a bowling ball rolling through a field of marbles, moving perfectly straight ahead. We can observe this directly. This historical cloud chamber photograph captures alpha particle emissions. Notice the stark, perfectly unbending white lines radiating outward. There is no random scattering or zigzagging here. There is one rare exception. Discovered by Ernest Rutherford, an alpha particle will occasionally strike a target nucleus head-on, causing a sharp deflection. But because the nucleus is so small, this Rutherford scattering happens in less than 1% of interactions. For the other 99%, the particle's mass guarantees a straight, linear path, carving a highly predictable and concentrated channel for energy deposition. Zooming into the atomic scale, this vector graphic illustrates the primary interaction force at play. The +2 alpha particle asserts an intense Coulomb attraction on the stationary -1 orbital electrons as it passes by. The dominant mechanism here is direct ionization. The alpha particle's attractive force is strong enough to rip an electron entirely out of its atomic orbit. This leaves behind a free electron and a positively charged atom, a combination defined as an ion pair. If the alpha particle passes at a slightly greater distance, a secondary interaction occurs, excitation. The attractive force pulls an electron into a higher, wider orbit, but doesn't quite detach it. That excited electron quickly drops back down to its ground state, venting the excess energy it absorbed as an ultraviolet or X-ray photon. Physicists quantify this energy drain using a metric called linear energy transfer, or LET. Alpha particles have a high LET. In air, an alpha particle loses an average of 35 electron volts of kinetic energy for every single ion pair it creates. With its strong +2 charge, the particle rips away tens of thousands of electrons per millimeter of travel. This dense rate of ionization is exactly what rapidly drains the particle's kinetic energy and forces it to slow down. We can now resolve the paradox using this split-screen model. The top shows the particle's speed, while the bottom tracks its energy deposition. Immediately after emission, the alpha particle's velocity and kinetic energy are at their absolute maximum. Notice the residence time, the fraction of a second the alpha particle actually spends in the immediate vicinity of any single target atom. Because the particle is moving fast, its residence time is low. The attractive force simply has less time to act, resulting in a relatively low probability of ionization at the beginning of the track. But remember, every single ionization event that does occur costs the alpha particle 35 electron volts. This creates a mechanical feedback loop. As kinetic energy is depleted, the alpha particle's forward velocity drops. As it slows down, its residence time near the remaining target atoms drastically increases. That increased residence time gives the strong +2 Coulomb force more time to grab hold of nearby electrons, causing the probability of ionization to rise exponentially. This is the Bragg peak. It is the visual representation of that compounding feedback loop, a massive, localized spike in ion pair creation, detonating right before the particle completely runs out of forward momentum. The paradox is resolved. A slower alpha particle is a vastly more destructive ionizer, specifically because it finally has the time to exert its attractive force on the surrounding environment. So what happens at the exact moment the particle stops? Eventually, its kinetic energy drops entirely to the thermal energy level of the surrounding medium. At this thermal baseline, the particle no longer possesses the energy required to rip away electrons or cause excitation. Instead, its +2 charge captures 2 free electrons from its immediate environment. By neutralizing its charge, the dangerous alpha particle transforms into a completely stable, harmless helium atom. The sheer density of this energy transfer directly dictates the particle's macroscopic range. Because its linear energy transfer is so extreme, the alpha particle depletes its energy supply rapidly. A 5 mega-electron-volt alpha particle will only travel 3 to 5 centimeters in the air. In solid matter, like a sheet of paper or aluminum foil, its range is measured in mere micrometers. The alpha particle's intense ferocity is its own limiting factor. It burns through its energy too quickly to penetrate deeply into matter. We can see the practical application of this when high LET radiation strikes biological tissue. This microscopic cross-section of human skin shows living tissue protected by an outer layer of dead cells, the stratum corneum. An external alpha particle strikes this dead outer layer first. In tissue, its total track is restricted to just 40 to 50 micrometers. The Bragg peak detonates its remaining energy here, neutralizing into inert helium before ever reaching the living tissue beneath. Alpha radiation's intrinsic mass and charge create a mathematically predictable concentrated energy spike. This concentrated destruction guarantees its short, easily shielded lifespan.